So now we're continuing with our circular motion examples, looking at harder problems. So let's begin with our first one straight away. We're going to begin with case 3. So this is kind of like a continuation of last video. Case 3, we're going to look at something called optimum banking angle. What I mean by optimum banking angle is, let me just draw a picture here because it makes the most sense. If I have almost like a racetrack, oops, that's not a circle, a racetrack, this is probably a better circle, and that's basically like a tilted, not a tilted, but like the sides of the roads are kind of like curving inwards, so it's something like a triangle here, and it's like curving like that, right? So the car would like go along this road, something like that. That's the basic idea of the setup for this problem. So let's actually pretend I have like a car here, and let's say the car is like on its side right here. Let's say it's right here in this location. It doesn't really matter the location, more so the idea of what I'm trying to get at, which is optimum banking. So we have a angle here, and we want to basically find what is the optimum speed the car must go along this path. And there's actually 3 cases that can happen. If it's too fast, so we'll look at the fast one, the car will actually start driving away from the circle. In other words, there's going to be a friction force, and no one likes friction, especially when you're worrying about speed. And then we have the normal force and the weight, right? The normal force and the weight. What happens if you're going too slow? If you're going too slow, it's actually going to start going in towards the circle, so friction's pointing the opposite direction. And no one likes friction, right? And then you have the other 2 forces right here. So there should be a middle ground. In other words, the optimum speed, that there is no friction, so that there's only 2 forces acting on this body, which is the normal force and the weight. This is the optimum speed at a specific angle. So this is the optimum banking angle. And this is applications actually used with race car drivers, because the racetrack is actually something like this, where it's kind of curved along. So they want to find optimum speed and something that does not have a lot of friction with respect to the radial direction, because that actually slows you down. So let's start looking at the forces. We're mostly going to look at this one, because the second diagram, because that actually tells us a lot more, right? We know that there should be a normal force here, normal force, and then the weight. So let's actually now look at a free body diagram of that specific thing right here. So now what's the angle, right? The angle is, we can't use the tilted axis because we're talking about centripetal force. So we're going to actually have to think of a different way to break down the normal force. The way we do that, let's see. Let me try to draw a diagram here, kind of like a side geometry work. If I have a object here, so let's say I have an object here and the force is going down. Let me scroll down. There we go. And I have something that's the weight that's pointing down, right? This is the weight, and this is the normal force. I'm going to actually continue that normal force. And this is the angle. I'm going to try to prove that this angle here is here. And the way we do that is simple. This is the normal force, so it has to be perpendicular to the surface. And this whole, right here, this whole thing has to be 180 degrees. It has to be, because that's a supplementary, it makes 180, it's a straight line. 180 is equal to this angle plus 90, and then what is, here, let me just erase this. What is this angle right here, right? The sum of these 3 angles should be 180. This angle is precisely 90 minus theta. So we're going to add 90 minus theta. The thetas cancel out and we're left with 180, right? So that must mean that this is the angle. So back to our thing right here. If this is the angle, then we can break it down into 2 parts. This is the normal cosine, and this should be the normal sine. And this is the weight, right? So that's our free body diagram. So now we're going to look at Newton's second law. With respect to the z, it is not moving because it's optimum banking angle. If it's not optimum banking angle, there's actually going to be some acceleration here, and we don't want that. We want it to be optimum. So we actually have normal cosine, which is something unusual. We don't really see normal cosine. We usually see mg cosine, the weight cosine instead, especially with inclined planes. So the normal is equal to, not the normal cosine of the angle is equal to mg. In other words, the normal is equal to the mg divided by cosine theta. And now we look at the radial direction, which is equal to mv squared over r. And now the thing that's supplying the radial direction, if you look at this free body diagram again up here, is the normal sine. So this is the thing that's supplying centripetal force. So normal sine theta is equal to mv squared over r. And then kind of like the conical pendulum question, we can actually substitute here and we actually get a result that's very similar. Mg sine divided by cosine is equal to mv squared over r. In other words, the masses cancel and this turns into the tangent. So we actually get a very similar, pretty much the same exact thing, but just in a different context. So it's v squared over rg. And then I guess if you want to find the speed, because that's typically the case, I'm going to draw an arrow here. We multiply both sides by rg and just take the square root. So we're left with the speed of the car that gives it the optimum speed should be rg times the tangent of whatever the angle of the incline is. Alright, so whatever it is, you just plug it in and you can find the best speed you should take to have no friction. We're going to do another example. Now we want to look at motion in a vertical circle, right? All our previous examples dealt with horizontal stuff. Now we're going to actually look at vertical. And this is kind of actually a little bit more difficult than thinking about horizontal, because it actually it does matter where we place our particle, because it does experience different things at different times. So here I have a circle, and what I want to do is you can go about it two ways. There's actually two cases of a vertical circle. You can have either the tension force applying it, so such as a string attached to a ball, or you can picture it like a loop-the-loop on a roller coaster where it's the normal force applying the thing. We're just going to go ahead and do the normal force. So pretend you are kind of like on a roller coaster and you are going around the circle. We're going to start with what happens when we're at the bottom of the circle in circular motion. And one thing about this is actually we don't have to worry about a side view of it, because it's not going to help us at all. So we have our weight and we have our normal force here, and it doesn't seem like much, but that's actually all there is to it. So now actually the only thing we can analyze is the radial direction. So mv squared over r, whatever r is. And then we just want to define the inwards as positive, right? So anything here is positive, anything outwards is positive. So we actually get n minus mg, because mg is actually pointing outwards from the circle, is equal to mv squared over r. And then the masses actually don't cancel in this case. I'm going to solve for normal force, which is equal to mg plus mv squared over r. And I guess I'll solve for the normal force just to see what it's like. And we're going to make a comparison later of this equation and the next equation I'm going to do right now. So now let's actually consider what happens when it is up at the top. So when you're halfway around the loop, what is actually happening now? So I'm going to do it a little bit to the right here. We have two forces, we do have two forces again. We have the normal force here, but now the gravity, or the weight of the object, is actually pointing in the same direction. So this is our second case, which is equal to mv squared over r, right? They're both pointing inwards, so I'm going to say they're both a positive force. Oops, let me write it a little bit lower so I have more space. N plus mg equals mv squared over r. In other words, n is equal to m. I'm going to write this term first, minus mg, and then we can factor it out. Let's see, n equals m. Let me actually write it in green, since this is our final result. N equals m v squared over r minus g. And actually I'm going to rewrite this just to make it helpful in our comparison. This was plus g, since I can just switch them because commutative property. So now we see that there's actually a small difference here. One has a plus and one has a minus, right? So what does that mean? That means when you're here at you experience, let me see. If you are at the bottom, let's actually start at the bottom. So in this first case, where we're at the bottom of the circle, just imagine us, I guess imagine our roller coaster coming from here and then actually going right here and taking another loop, right? We're just going to see it in terms of that. What this basically tells us, since normal force is kind of like a measure of our like fake weight, or like the weight we feel, called the apparent weight, we see that through this equation we actually feel a normal force that is a lot heavier than our own weight. So we feel something that's a lot heavier. This is when you get that feeling when you like are being pushed to like the ground a lot more, because of this normal forces being so I guess so big. It's the apparent weight. And then in contrast, this one's actually you're experiencing something less than your weight, so you kind of feel almost you're getting to a point where it's almost weightless. So that's why that's what the significance of the minus sign here and what is the significance of the plus sign is. Actually, we can feel it when we're on a roller coaster. If you're ever on a loop-to-loop, at the bottom you just feel a lot heavier because of this equation right here. And at the top you kind of feel a little bit lighter, but again it happens all so quickly, so it's kind of hard to pinpoint exactly when that feels. But maybe next time you're on a roller coaster, you might actually want to see if that is the case. Do you feel heavier at the bottom when you're finished with the loop, and then do you feel a little bit lighter at the top? That's something you can, I guess, try next time you're on a roller coaster. So that's it for circular motion. So just a quick review with the idea of circular motion. We need to write a free body diagram such that we have a circular or a centripetal force. And remember that centripetal force has to be something. It has to be either, like, could be like a normal force, it could be a tension force, it could be even a friction force, right? But there's no such thing as a centripetal force. It has to be something acting as the centripetal force. I want to make that clear distinction. And notice that the centripetal forces has to be pointing towards the center. It can't be pointed kind of at the center and a little bit away. That means you have to break the force into components, and you might have to use some geometry to find that out. So that's it for, I guess that's it for the whole free body diagram series. It's been a 6-part journey of going through many different cases of free body diagrams, and hopefully what you take away from this series is just kind of the process or the idea of how you tackle these types of problems, not so of the formulas that you have to memorize now, because no, I'm not going to remember these formulas. I'm going to remember how to get there, but I'm not going to remember the end result. And I can always find the end result if I know how to get there in the first place. So that's the key takeaway from this 6-part series, and you see it in so many different occurrences. So that's it for free body diagrams, and we're just going to continue finishing up dynamics in the next lesson.